Okay, so what we'll move on to now is geometry, what I'm calling geometry of the multivariate normal. So we'll come back to the multivariate normal later. But this is not going through everything that we need to do theoretically about it. It's splitting off a particular issue about how its contours look. So let's remember I'm going to write MB. I'm going to write this so often. In the notes, I try and spell it out, but when I write by hand, I'll be writing MBN quite a lot from now on. Okay. So recall PDF and MGF are these things. So there's normal, sometimes indexed with P, that has an argument of vector F, and let me move this left. Just get into out of space. Okay. So it's normal P, which has an argument X and parameters mu with a sigma, and that's 1 over root of 2 pi to the P determinant of the sigma, and then e to the minus a half. Okay. So we went through this before. That's column times P by P times, sorry, that's row, length P row times P by P times length 3 column. That means this is a scalar. So the F is a scale, this M is a scalar function, scalar value function that takes a vector valued argument. Okay. Now it's going to be the same for the MGF. The MGF is going to be a scalar value function taking a vector valued argument. So the MGF takes a vector argument T and takes this much nicer, simpler form. So one of the key concepts in geometry is distance. So I'm going to call that, and I'll call that equation for 1, 1. Yeah. Okay. Okay, so what does univariate distance mean? So let's consider something like this, where we've got X and we've got on the Y-axis a normal of X given 0 sigma squared, right? And so what you'll probably remember is that is that you have a certain percentage of the multivariate normal observations within 1 standard deviation, within 2 standard deviations, and so on and so on. Yeah. So in some fields, people will say, "Oh yes, this is a 3 sigma event. This is a 4 sigma event." Right? That means that it's like, so if it's a 2 sigma event, it occurs less than 1 in 20 times you do the measurement. Yeah. So how can you think of that? Well, so more formally, the mean, mu, and standard deviation sigma. So the distance of a point in sigmas or standard deviations is going to be so distance of x is the absolute value. So that's by that I mean abs of u for u equal x minus mu over sigma. Okay. And so that's a rule for calculating how many sigmas out an observation is, given that your model is it should have a mean, that process should have a mean mu and a sigma, right? And that's sort of an objective measure that doesn't depend on units, right? So it doesn't depend on whether what you've measured is measured in you know, pounds and ounces or kilograms or feet or meters or whatever, yeah. And so it's going to turn out that the multivariate version of that, this is the square root of the variance, right? It's going to be the matrix square root, the inverse matrix square root that's going to play the role of 1 over sigma, okay? And that's so that's spoiler alert, right? So lots, Mahalanobis distance, an enormous amount of very important statistical work done by Indians, and in India, Mahalanobis is one such. We're encouraged to quite correctly to highlight these things, right? Not all of stats was done by Fisher, right? It was all, there were lots of contributions from all over the world. And it's interesting to look at the history of some of these people who made contributions and other things that they did and thought about and what was motivating. So I can't really give a history of science course, but I just encourage you to, you know, when you see interesting names of people, it can be worth looking them up. So student of students T wasn't really student, it was someone who signed a paper from student, right? So there's a lot of interesting history of the field as well. I don't plan to go into, but I think can be enjoyable to read while you're learning it. Okay, so we'll need to do get some preliminary results. Okay, so the main one is going to be what happens to multivariate random vectors under linear transformations. Okay. So let x go like normal p mu sigma, yeah, and let a be a constant let p vector and a be a constant P by P matrix, yeah, then Y, which is equal to the matrix on x minus A, is normal itself, but with mean equal to A on mu minus A, and covariance equal to A sigma A transpose. Okay. So this is the behavior of a multivariate normal random vector under a linear transformation like this. So you shift with a vector and then multiplication by a P by P matrix. Okay. Okay, so the way we're going to do this is consider the moment generating function of y, which is the expected value of e to the t y. That's from definition to I1. Yeah. So we're going to write out the expectation. So that's the integral over Rp T. And then we know what y is, yeah? So y is a on x minus a on normal of x, yeah? Given you sigma, yeah? So that's write out the expectation, okay? So first thing we can do is we can pull out a bit of this that doesn't depend on the x that we're integrating, yeah? So that's equal to e to the minus t a, yeah? That doesn't depend on the x that we're integrating over, times the integral over Rp of e to the t transpose a x, yeah? And then I'm just going to call this f of x to avoid writing everything out, yeah? So of x dp x, yeah? And then if you look at this thing here is equal to the moment generating function of x evaluated at a transpose t, yeah? So this is equal to e to the minus t transpose a on the moment generating function of x, but evaluated at a transpose t, yeah? So that's the definition of the moment generating function of x. It's just I wrap these up, yeah? And these are a new t prime, which is equal to a transpose t, yeah? When I scribble on things. So you could say there's a new t tilde, yeah, which is equal to a transpose t. So that's why it's the moment generating function, yeah. And then what we're going to do is put in, we know what this is, because we wrote it down there in equation 1.1. So this is equal to AA on E yeah. So that's the first bit, then plus a half of a transpose T. Okay, so that's substituting in, so that's from 411. Yeah. Then we're going to rearrange and group lots of terms. So that's equal to e to the t transpose on a u minus a. Yeah, so you can see that that's the a term with a minus in front of it, and then that's going to be t transpose a on u without a minus term. Yeah, plus a half on t transpose a and then what we're going to do is we'll say, well, look, this is my mu tilde, yeah, and this is my sigma tilde, and we're going to say equals MGF of a normal with mean and covariance as advertised, yeah. And that's what we wanted to show, because we're kind of just assuming throughout the course that we know what the MGF of the normal is, and you can go between MGFs and PGFs, right? The MGF is sufficient to define the random variable. Okay. So this is the important thing, that the mean goes like you'd expect, right? The covariance is not affected by shifting things around in the plane, which is what you'd expect, yeah. And it's that both dimensions of the covariance get that linear transformation applied to them. So it's not a terribly surprising result, but it's not, it's kind of what you'd expect when you think about linear transformations, but you know, it's worth showing and remembering, yeah. And so that's going to be, and what you should start thinking about is this is looking a bit like this here, yeah. Yeah, this is looking like it could be a matrix version of this, okay. And that's what we'll get on Tuesday, okay. So on Friday, tomorrow, we'll just do the problems 2. And I did ask, one of the problems in problem 2 is already showing that thing with the centering matrix is what we want, so that's not going to need to change. So yeah, we'll be going through that. We mainly stuff about centering matrix bias, that sort of thing. That's what's in problems 2. So we'll go through those tomorrow. And we'll probably go, I suppose tomorrow we should probably go through the problems 3 as well, right, where I show you some stuff about the exploratory data, because we'll probably have to do both of those in that go. So have a look at both of those before tomorrow. And then we'll spend most of next week in the lecture finishing off about the geometry of the multivariate normal. So are there any questions? No, so see you tomorrow then.